Good day. Today we're going to discuss the matrices and matrix operations. Rectangular arrays of real numbers arise in contexts other than as augmented matrices for linear systems. So in this discussion, we will begin to study matrices as objects on their own rights by defining operations of addition, subtraction, and multiplications on them. Okay, so let's have the matrix notation and terminology. Now, a matrix is a rectangular array of numbers. The numbers in the numbers in array is called the entries in the matrix. Okay, so a matrix with only one column is called column vector or column matrix. And the matrix with only one row is called a row vector or a row matrix. Okay, for example, if we have 2 by 1 matrix, it is called column vector. And if you have 1 by 4 matrix, it is called row vector. And a 1 by 1 matrix is both a row vector and a column vector. For example, let's say um, you have uh, in this illustration, you have this one. So as you can see, okay, here, this capital letter, okay, stands for a matrix. So we will use capital letters to denote matrices, and as for the entries, we are going to use lowercase letters. Say, um, when discussing matrices, it is common to refer to numerical quantities as scalars, unless stated otherwise. Scalars will be real numbers. Okay, so matrix brackets are often omitted from, let's say, a one by one matrices, making it impossible to tell, for example, whether let's say symbol 4 denotes a number 4 or matrix 4. This rarely causes problems because it is usually possible to tell which is meant from the context itself. Okay, now let's go back to this illustration. Um, the entry that occurs in row I and column J of a matrix A will be denoted by, uh, that's right, by small letter A sub I J. In therefore, a general 3 by 4 matrix would be written this one. Okay, so this one. And a general M by N matrix would be this one. Again, let me emphasize that in the subscript of the entry, the first number in the subscript would be our row, which is uh, I, and the second number in the subscript would be uh, our column. Okay, so you have row, so this one, and column. Okay, the I and the J. Okay, so when a compact notation is desired, the preceding matrix can be written this one or this one. Okay. The first notion or the first notation being used when it is important in the discussion to know the size, and the second notation, okay, being used when the size need not to be emphasized. Usually, we will match the letter denoting a matrix with with the letter denoting its entries. Therefore, as the matrix B, okay, capital letter B, we would generally use the small letter b sub ij for the entries in the row I and column j. And for the matrix C, we will use the notation small letter c sub ij. The um, the entry in the row I and column j of the matrix A is uh, also commonly denoted by the symbol, this one, this symbol. Therefore, for the matrix above, okay, for this matrix, okay, for this matrix, we can denote this one as this, okay, symbol. Okay. Okay, for example, let's have matrix A with entries 2, 7, negative 3, 0. Okay, if we are going to look for a matrix A sub 1, 1, it means to say that you have 2. Then let's say matrix A sub, let's say 1, 2, then you have negative 3. It seems that I wrongly mentioned this would be the row, this would be the row, and this would be the column. Okay, I stand corrected. So this would be the row and the column. Okay, so the row and column vectors are of special importance, and it is a common practice to denote them by a boldface lowercase letters rather than capital letters. So this one. So you have bold face lowercase letters. Okay, for such matrices, double subscripting of the entries is unnecessary. Therefore, the general 1 by n row vector A and a general m by 1 column vector B would be written as this one. Okay. Now, the matrix A with n rows and n columns is called a square matrix of order n. And so this one. And these entries with diagonal is called the main diagonal of A. Okay. So let's have operations on matrices. So far, we have used matrices to abbreviate the work in solving systems of linear equations. For other applications, it is desirable to develop an arithmetic of matrices, in which matrices can be added, subtracted, and multiplied in a useful way. So we have this definition. Two matrices are defined to be equal if they have the same size and their corresponding entries are equal. Okay, so the equality of two matrices, let's say matrix A, okay, and matrix B, this illustration, okay, of the same size can be expressed either by writing this one or by writing this one. So they are the same. Where it is understood that the equalities holds for all values of I and j. Okay. Um, for example, okay, consider the matrices A, B, and C. Okay. Now, in this case, if x is equal to 5, then we could say that matrix A is equal to matrix B. But for all other values of x, matrices A and B are not equal, since not all of their corresponding entries are equal. And for the third matrix, okay, there is no value for x for which uh, matrix A would be equal to matrix C, since matrix A and matrix C have different sizes. Okay, so let's have definition 3. If matrix A and B are matrices of the same size, then the sum matrix A plus B is the matrix obtained by adding the entries of B to the corresponding entries of A, and the difference, matrix A minus B, is the matrix obtained by subtracting the entries of B from the corresponding entries of A. Matrices of different sizes cannot be added or subtracted. Okay, so in uh, matrix notation, so if matrix A is equal to A sub ij and matrix B is equal to B sub ij have the same size, then we could have this one, the A plus B sub ij is equal to the matrix A ij plus matrix B ij, which is equal to, you have small letter A sub ij plus small letter B ij. And the same goes with the subtraction. Okay. So let's have an example. So consider the matrices A, B, and C. If we are going to have uh, matrix A plus B, then we are just going to add the entries. So in this case, so you have 2 plus negative 4 is negative 2. Negative 1 plus 2 is 1. Then you have 4 plus 3 is 7, and so on. Let's just going to have uh, write that one immediately. So you have 4, 5, 4. Here you have 2, 2, 3. And you have 0, 3, 5. Same goes when we are going to have A minus B. So you have 2 minus negative 4, that would be 6. Then you have negative 1 minus 2 is negative 3. Then you have 4 minus 3 is 1, and so on. So you have 2, negative 5, 2. Here you have negative 2, 2, 5, negative 4, 11, negative 5. So the expressions A plus C, B plus C, and A minus C and B minus C are undefined because they are not on the same size. Okay, so definition 4. If matrix A is any matrix and C is any scalar, the product CA is the matrix obtained by multiplying each entry of the matrix A by C. The matrix CA is said to be scalar multiple of A. Okay, I just forgot to delete this one. Okay, so for example, you have matrix A, and then let's say you have 2A, then that would be 2 times 2, 3, 4, 1, 3, 1. That would be equal to 4, 6, 8, 2, 6, 2. Okay, let's have definition 5. If matrix A is an M by R matrix and matrix B is an R by N matrix, then the product AB is the matrix M by N matrix whose entries are determined as follows. To find the entry in row I and column J of AB, single out the row I from the matrix A and column J for the matrix B. Multiply the corresponding entries from the row and the column together, and then add up the resulting products. Okay, so let's have an example. So consider this one. You have matrix A and matrix B. Okay, so since matrix A is 2 by 3 matrix and matrix B is 3 by 4 matrix, the product AB would be a 2 by 4 matrix. To determine the entries in row 2 and column 3 of AB, we will single out 2 from the A and column 3 from B. Then that's how we are going to get. Okay, Ken, if you have AB, okay, let's just solve everything. You have 2, wrong. It should be 1. 1, 2, 2, 6, 4, 0. Okay, by 4, 0, 2. You have 1, negative 1, 7, 4, 3, 5, 3, 1, 2. Okay, so this would be equal to uh, the, if we are going to get the first element, the 1, 1 here, we are just going to, okay, multiply, okay, 1 by 4, 2 by 0, and 4 by 2, and add them together. Okay, again, you have uh, 4, 1 by 1 times 4, plus 2 by 2 plus 0, plus 4 by 2, that would be equal to 12. Okay, now if we are going to get the element 1, 2, then you have, what you're going to do is you have 1 times 1, then 2 times negative 3, then 4 times 7, then add them together. So you have here 1, 1 times 1 minus 2 times 1 plus 4 times 7 is equal to 27. Then if we are going to have the 1 3, then you have uh, 1 times 4 plus 2 times 3 times plus 4 times 5, and that would be equal to 30. Then for the 1 4, so you have 1 times 3 plus 2 times 1 plus 4 times 2, which is equal to um, 13. Okay, 13. Then you have for the next, you have uh, 2 times 4, 2 times 4 plus uh, 6 times 0 plus 0 times 2, which is equal to 8. Then you have 2 times 4, 2 times 1 mm, minus 6 times 1, then plus 0 times 7, which is equal to negative 4. Negative 4. Then you have the next is uh, you have for the third entry, so you have 2 times 4 plus 6 times 3 plus 0 times 5 is equal to 26. It's 26. Then for the last one, so you have 3 times 2 plus 6 times 1 plus 0 times 2 is equal to 12. Okay, and that's our matrix. This is 13. Okay, so let's have partition matrices. Um, a matrix can be subdivided or partitioned into smaller matrices by uh, inserting uh, horizontal and vertical rules between the selected rows and columns. For example, you have this illustration, three what you call this one, three possible partitions, okay, of a general 3 by 4 matrix A. The first, okay, this one um, is partitioned of matrix A into four submatrices. You have matrix A11, you have A12, A21, and A22. The second one, okay, is a partition of matrix A into its row vectors. You have R1, R2, and R3. And the third partition, okay, into its column vectors C sub 1, C sub 2, C sub 3, and C sub 4. Okay, so let's have matrix multiplication by columns and by rows. So partitioning has many uses, one of which is the finding particular rows or columns of a matrix product AB without computing the entire product. Specifically, okay, we have formulas whose um, proof are left. Okay, however, it needs to be shown. Okay, so that it can be seen that how individual column vectors of AB can be obtained by partitioning B into column vectors, and how individual rows vectors of AB can be obtained by partitioning matrix A into row vectors. Okay, so we have this one, the AB, this one, okay. AB, okay, okay, computed column by column, and this one, it is computed row by row. In uh, in words, these formulas are stated. You have the jth column vector of AB is equal to 8 times the jth column vectors of B. And then the ith row vector of AB is actually the ith row vector of A times the B. Okay, so let's have matrix products as linear combination. Okay, so let's have the definition. Okay, if the matrix A to A sub R, okay, are matrices of the same size, and C sub 1, C sub 2 up to C sub R are scalars, then the expressions of the form C sub 1, A sub 1 plus uh, it should be let me correct, it should be C sub 1, A sub 1 plus C sub 2. This should be 2, 2, 2, 2R. That would be R. Okay, it's called the linear combination of A sub 1 to A sub R with the coefficient C sub 1, C sub 2 to C sub R. Okay. So we have here theorem 3.1, 1.3 time point 1. If matrix A is m by n matrix, and if X is a n by 1 column vector, then the product AX can be expressed as a linear combination of the column vectors of A in which the coefficients are the entries of X. So we have an example. So the matrix product, okay, you have uh, that one is equal to 1, negative 9, 3. Can be written the following linear combinations. Okay, we could have we could have that can be written as this would be our first 2 times negative 1, 1, 2, okay, minus 1, and you have 3, 2, 1 plus 3, 2, negative 3, negative 2. Okay. So the 2, negative 1, 3 is actually this one. Okay. Which is equal to, you have 1, negative 9, negative 3. Okay. And then for the next, okay, if you have AB, okay, which is equal to that one, it follows that uh, you have here you have 12 8 would be equal to 4 times 1 2 plus 0 times 2 6 plus 2 times 4 0. And let's say you have 27 negative 4. It follows that uh, you have 1 2 minus you have 2 6 plus 7 4 0 and so on. Okay, so matrix form of a linear system. Um, Matrix multiplication has an important application to system of linear equations. Okay, for example, you have consider a system of m linear equations and n unknowns. So you have that one. Okay, so since two matrices are equal if and only if their corresponding entries are equal, we can replace the m equations in this system by the single matrix equation. So that one. Okay. The m by 1 matrix on the left side of this equation can be written as the product to give that one. We can, if we can designate these matrices by A, X, and B, respectively, um, then we can replace the original system of n equations in n unknowns. Okay, has been replaced by a single matrix equation. That one. Okay, ax equals b. The matrix A in this equation is called coefficient matrix of the system. The augmented matrix of the system is obtained by adjoining uh, the B to A as the last column. So, in other words, that would be our augmented matrix. Okay. Now, take note that the vertical bar in the matrix is a convenient way to separate A from the matrix A from B visually. It has no mathematical significance. Okay, so let's have transpose of a matrix. So let's have definition. If matrix A is any m by n matrix, then the transpose of A, denoted by A raised to t, okay, is defined to be the matrix that results by interchanging the rows and columns of A. That is, the first column of the uh, transpose matrix A is the first row of A, and the second column of the transpose of A is the second row of the matrix A, and so forth. Okay, for example, okay, the followings are some examples of matrices and then and of their transposes. Okay, so you have here this illustration, the A uh, a sub I is the same. However, the a sub 2 here, okay, is the a sub 2 here. As you can see, they're just interchanged. Okay, same goes with this one, okay, with B and C and D. Okay, so observe that um, not only the columns of the transpose of A, the rows of A, but the rows of the transpose of A are the columns of the matrix A. Therefore, the entry in the row I and um, column J of the transpose A is the entry in row J and column I of matrix A. Okay. So, in other words, if we are going to write that one, then you have the transpose of A. Let me correct. Okay, so the transpose of A, okay, sub ij is equal to the matrix A ji. Okay, so let's have the definition 8. If A is a square matrix, then the trace of A, denoted by T or A, is defined to be the sum of the entries on the main diagonal of A. The trace of A is defined if A is wrong. The trace of A is undefined if A is not a square matrix. Okay, so for example, you have this one. You have matrix A and matrix B. So in other words, our transpose of A would be the sum of the diagonal. Then you have would be equal to A sub 1 1 plus A sub 2 2 plus A sub 3 3. And of course, the transpose of B would be the sum of the main diagonal. So you have negative 1 plus 5 plus 7 plus 0 equals, that would be 11. Okay, so that's all for the topic of matrices and matrix operations.